here we go. This is lesson 3.5, collect like terms. So we already watched a math antics video to help us out as far as knowing, okay, if I'm dealing with x squareds, I can group the x squareds together. If I'm dealing with x squareds and x's, I can't group them together, but I can group all the x's together, and I can group all the x squareds together, and I can group all the unit tiles together. So this lesson is just going to confirm a lot of things that we're already aware of. And the first example is a word problem. We're going to put our tiles to work in a real-life situation, kind of. So we're dealing with Crystal. Crystal bought a used Sea-Doo with her summer earnings. Unfortunately, it needs some repairs before she can use it. So we're going to model each repair using algebra tiles and then write an expression to describe it. So in A, for example 1, we're using algebra tiles to express what's happening, and you can see that little grid that shows you she needs a new alternator and she needs a new fuel pump. And, well, the cost per part, do we know that? The cost per part?
200 and 100.
Yeah, we know that. It's the number alternator costs $200 and the fuel pump costs $100. So since that's a known value, why don't we let each unit tile, that's these little guys, be $100. Okay, so we're going to say, okay, if we have $100, it's 1 unit tile, $200 is 2 unit tiles, $300 is 3 unit tiles. And then there's this labor cost. Now, up to this point, we don't know how much labor is going to cost. We know how many hours of labor it will be, 4 for the alternator and 3 hours of work for the fuel pump. But we don't know how much labor costs. So we could represent that using a variable. So let's let each x tile, which looks like this, be the cost of 1 hour of labor. Alright, so we've got our two things dealt with here. The money that we actually know, 1 unit is $100, and the x is the unknown cost of labor. And now we need to model the repairs using algebra tiles. So go ahead and try that on your own. Model each repair. So we've got the alternator, and we've got the fuel pump. Once you've tried that on your own, you can just double check up here. We know that the alternator for the cost of parts is going to be just $200. So you should have 2 of these unit tiles, each of them worth $100. And it's going to cost 4 hours of labor. So we have 4 unknown values here. That's 4 hours of labor. These are all colored in X bars. They're positive X. Then for the fuel pump, the part costs $100, and it costs 3 hours of labor. However you arrange that, something like that is okay. If you want to do it all in a row, that's fine too. Good. Now, an expression for each repair. Well, the alternator, we have 200 and plus 4x. Right? What do we have for the fuel pump?
100 plus 3x.
100 plus 3x. Good job. B. Find a simplified expression for both repairs together. Now this is when we're getting into the heart of what this lesson is about. We're kind of adding and subtracting. We're grouping like terms. So can I group these guys all together to represent the total cost of the repairs?
Yeah.
Yeah, I could. So let's draw a picture that represents that. How many unit tiles will I have? 3. And how many x tiles?
7.
And I'm making sure to kind of color them in because we remember that our white tiles or our blank tiles were negative numbers. Right now we're adding all positive amounts. And could we come up with an algebraic expression to represent what we did with our algebra tiles? Yeah, it's not really that hard. How many hundreds do we have?
300
We have 300, and how many x's?
plus 7x.
7x. Now here's something we need to look at. What if I drew a line across here and put a plus sign? Does that look like what we just did? Really, all we did was we took the unit tiles and added them up to get 300, and then we took all our x's, we added them up to get 7x. We grouped like terms. These guys are like terms, and these guys are like terms, so we can put them together. Okay? That's what we're talking about today. Now, in C, it says, calculate the total repair cost if the mechanic were to charge $50 per hour for labor. Well, we have our total repair cost right here as an algebraic expression. It's 300 plus 7x. And what did x represent?
50.
X represents the cost of 1 hour of labor, and now we're told in C that that's going to be $50. So we work vertically down, put an equal sign so that it's nice and neat, and wherever we see an x, we're going to replace it by 50. Now we know the value of x. We didn't before, but now we know what it is, so we can just sub it in. We're just left with numbers here, and we used bedmass to put this all together. So what do I have to do first?
Times
I have to do my multiplication, 7 times 50, so I'll take 300 down. 7 times 50 is 350, and now I can add, leaving us with a total repair cost of $650. Crystal will pay $650 to have her Sea-Doo repaired. Alright, we used algebra tiles to, it's a concrete material, you can move it around with your hands to model the situation. Then we drew it out, we added it up by grouping like terms to create an algebraic expression that would represent the total cost of repairs. And then we were told that labor was $50 an hour, so we subbed that in and solved to see that Crystal will pay $650. In the next example, we're just identifying like and unlike terms. Again, this is familiar from the video that we watched, but right under that sentence, identify the like terms in each group. We're just going to put a little note as to what like terms are. So, like terms are terms that have identical variables. Identical variables. If terms have identical variables, we can combine these terms. Okay, so here we have more practice with that. In A, you don't have any of them written there, but we're going to identify the like terms in the group of terms in A, and just write this. It's 2x, comma, 2, comma, 5x, comma, 3xy, comma, 3x. And we have to identify the terms that are like terms. Well, somebody go ahead and take a shot at it.
2x and 5x.
So 2x and 2x and 5x are like terms because they both have an identical variable, and 3x is also a like term. Why is this one not included in the group? Because its variable is x times y, not the same as x. What about if we added a term, I don't know, x squared? He's got an x in it. Is that included now? No, it's not. X squared is different than x. Okay? X squared is different from x. That's why it's represented by different tiles in your algebra tiles. Good job. Okay. Erase that note. Let's go with B. B, the list of terms is 4a squared, comma, 2a, comma, negative a squared, comma, a cubed, and a squared b. Somebody knew what are the like terms? Olivia.
4a squared and
You got 4a squared and negative a squared. Nothing else gets added to the list. Yes, this has an a in it, but a squared is different from a. This has a cubed, so it actually has a factor of a squared in it, but it's not the same. It's different again. If it has a different degree, it's a different variable. And this guy has a squared in it, but he also has a b. Okay, in order for them to be like terms, the exponents on all variables must be identical as well. Okay?
So wait, why is that A3 not? Why is that A3 not part of the?
Because it's what's it called, cube.
Well, what about the quotient law?
Just like x to the power of 1 and x to the power of 2 are not the same variable, x to the power of 2 is not the same as x to the power of 3 is not the same as x to the power of 4. Okay, so the exponents on all variables must also be identical. So we're looking for the letter to be the same, and then also looking for the exponent to be the same.
What about the quotient law on these 3? Can't you add those together?
Right now we're just listing terms. Here's a term, here's a term, here's a term, here's a term. They're not connected by addition or subtraction or anything like that. We're just listing terms and saying, okay, which of these terms are actually like terms? Which of these terms has the exact same variable? If you're going to ask a question, make sure you listen to the answer. Yeah? Instead of looking around and... Thanks. C, our list of terms. 3u squared, negative 4uv, 6, 2u squared, 1/2 v, and negative 5. Somebody knew what are our group of like terms. 3u squared and 2u squared. We've identified they both have the same letter and the same exponent, u squared. That's like terms. Is there another group of like terms here?
5, negative 5, and 6.
Ah. 6 and negative 5 are both, what are they called? Constants, right? Yes, they're integers. When we're talking about polynomials, we'll call them the constant. So they could be grouped together, right? If we were to have them in a string of a polynomial, then they would just group together. We'd have 6 positive unit squares, and we'd have 5 negative unit squares. We'd be left with 1 positive unit square by the end of it. Good. Not too difficult there. You guys are getting pretty good at that. Let's look at the next example, example 3. And if you have a little bit of space just above example 3, you can say this. To simplify a polynomial, if you don't have any space just above it, then just write it just under that line. To simplify a polynomial expression, add or subtract like terms. Okay, that's exactly what we saw in the video yesterday. He said, oh, sometimes there's extra terms in a polynomial, but since they have like terms, they have identical variables, we can just add them together in order to simplify. So the first one that we have here is a 4x plus 3x. Do we have like terms?
Yes.
Yeah. So let's draw it out quick. We're going to draw it using our algebra tiles quick. We've got 4 x's. And we've got 3 x's. All positive. And all we need to do is add them up. How many x's do we have altogether? 7x. Okay? Looking at example B. In example B, we have 4x plus 3 plus 2x plus 5. Okay, we can draw that as well. We're going to have 4 x's. Three unit tiles, 3 ones. And then we're going to have 2 more x's. And 5 more ones. Well, what can I group together? Yeah, it's easy to see. We're going to group our x tiles, right? Our 4x and our 2x for a total of how many x's? 6x. And we're going to group our unit tiles, 3 here and 5 here, 3 plus 5 for a total of 8 unit tiles. Not too difficult. Good. Moving on to example 4. Now we've added them. Okay. In example 4, we're going to be subtracting them.
Wait, why can't you just add?
Okay. Example 4, we're going to be subtracting like terms. I'm going to show you a couple different ways to think about it. Our first example is pretty straightforward. You have 8x minus 3x. So we can represent our 8 x's. Example 4, yeah.
So we're on example 4.
Now example 4, but it's the same thing.
1, 2, 3, 4, 5, 6, 7, 8. So we got 8 x's here. Make sure we color them all in, because now we're going to be dealing with some negative tiles, which are going to be left blank. It's white. We have 8 positive tiles, and now we need to remember this negative sign sticks with this term. Okay? So what we actually have here, there's 2 different ways. The one way that's really easy right off the top to do this one would be to, if you have 8 x's and you need to take away 3, well, you know, just like in elementary school when you were counting counters, you would just strike out 3 of them, and you'd be left with 5 of them. That's pretty easy to see. 8x minus 3x is 5x. And that's a good way to think about this one. I'm going to do it a different way because it's going to help us with more complicated problems. We have 8 filled in x tiles. We have 3 blank x tiles. You'll see why I did it this way when we get on to the next example. But basically what we're saying is, okay, these guys add up to 0. So they don't count. They all kind of just cancel each other out. And we're left with 5x. Okay, 5x tiles.
Isn't this what we did with dividing like before? Like we just divide them?
Nope, you're talking about exponent laws. Yeah, don't mix up the two. Right now we're just talking about the coefficients are getting subtracted. We're finding the difference in how many x tiles we have using this strategy here. Okay, the next example is going to demonstrate why we do it this way, and it is 2x minus 5x. So I have two positive x's, which we can represent using two filled in bars. And now what would happen if I started crossing out 5 x's? I'd run out, okay? And it might be difficult in this problem. You can see the answer is going to be negative 3x, but it might be difficult to see that. So instead what we do is we just draw 5 negative tiles. You will be expected to do this without tiles at some point, just not in this lesson. So we have 5 negative tiles, which means these guys just become 0. They cancel each other out, and what are we left with? Negative 3x tiles. Okay? 3 negative x tiles, however you want to say it. Good. And a little note at the end of that page, adding and subtracting to simplify an algebraic expression, adding and subtracting in order to simplify an algebraic expression is called, what's it called? What did we just do? What's the lesson called?
Subtract like terms.
Yeah, collecting like terms. And you can underline that. And we had our little note above here to simplify. You can underline the word simplify as well. And now that we're experts, we're going to get a little more complicated example. Again, we're still using, technically, the lesson would like you to use your algebra tiles. Okay, so if you're still not sure why you can't add x squareds and x's and 1's together, then continue using your algebra tiles because they'll clearly indicate that they're not the same, right? X's and 1's aren't the same. So if you are still struggling with that, please use your algebra tiles. Otherwise, drawing pictures is okay. That's what I'm doing for the sake of time. So we're on example 5, and we're going to collect like terms, and it's asking us to use algebra tiles to simplify each expression. Our first expression that we're going to simplify is 5k minus 3k minus 6 plus 3. Now you're probably thinking, oh, there's no x here, there's k. What do I do with the k?
It's the same thing as x.
Use it the
Just
same as an x.
Use it the same as an x. It's just another variable raised to the power of 1. So now you have your x bar, your x tile is actually a k tile. Go ahead and draw this one out, and then double check on the board to see that you've drawn correctly. Remember, the sign in front stays with the term. So I'll box kind of each term there for you, and go ahead and draw that. Check the board after you're done drawing.
So
Alright, it's not really important how you organized this, but you should be left with something like what I have here. You should have 5 filled in x tiles and 3 filled in unit tiles. Then you should have 3 blank x tiles and 6 blank unit tiles. And so now we can just do our little cancel out. You know, positive 3 and negative 3, that's 0. Leaving us with 2k. And over here in the unit tiles, we've got 3 positives, so we'll take away 3 negatives, leaving us with negative 3. Remember, that's the constant over here. So it's just -3. You don't have to say anything else. You don't have to say 3 units or 3 ones or 3 yada yada.
Oh, there was a minus sign. Was it not?
What is
Shouldn't we do 6 plus 3?
Like the brackets.
-6? There's our 6 negative tiles.
Yeah.
+3. There's our 3 positive tiles. B. The expression is 3c squared plus c minus 2 minus 5c minus 4c squared. Leave the space directly underneath blank and make sure you draw your tiles off to the right, okay, because I'm going to show one extra step here. So go ahead and draw it out.
What does thievius do?
Yes, good question. A c to the power of 1 would just be our x tile, in this case our c tile, which is just our bar, our stick, which I'm drawing here. And c squared is our x squared tile, our big block. It's a side length c times c. One more of these. And then minus 4 of these. Perfect world, all of my tiles would be properly proportioned. Okay. Now when we draw it out, this is why it's nice to use the physical algebra tiles. When we draw it out, it looks like a big mess. But what we really like to do is rearrange it so that all of the c squareds are next to each other and we can easily cancel out. And all of the x's or c's, are close to each other and we can easily cancel out. We could do that with algebra tiles. We could redraw this whole thing with all of these guys over here. But instead, I'm just going to show you how to do it algebraically. Remember that the sign in front of the term sticks with that term. So here we have 3c squared, and I'm going to look for my other c squared, and I'm going to bring him next, keeping the negative sign with him, so I know it's -4c squared. So that's next, -4c squared. Then I'm going to look for all of my terms that have c. Well, there's one, and there's one. Okay, I'm going to have plus c and -5c. And then I have one constant, which is just -2.
You have to group because I
You
did that.
just group it right away.
If you can see it
I
right
did it
away,
without grouping.
if you can see it right away, it's not a big deal. But problems do get more and more difficult as we move along. That's why we practice these things ahead of time. Okay, so now we can do our little adding and grouping thing. I notice here I've got 3 positives, so I'm just going to cross them out, which means I'm going to cross out 3 negatives, leaving me with -c squared. And I can see that right here. I've got 3 minus 4, that's going to be -1. -1c squareds is what we're dealing with. And then I have my c's. I have 1c and -5c. So they're going to leave me with how many? -4c. And my constant, he's just going to come down. He's the only one, -2. Okay, this is as reduced as it can be. Notice we have an invisible coefficient -1 here. If the coefficient is 1, you can just not write it, but you need to maintain the negative symbol to show that it's actually still one of these blank tiles and not one of these colored tiles. And we always typically want to write them in order of degree. So you can see that this is a 2nd degree, this is a 1st degree, this is a 0 degree. Okay? So note a simplified polynomial must be recorded in order of degree, comma, from greatest to least. So if you have a string of terms, x to the power of whatever, always start with the highest power of x first, and then the next, and then the next, and it'll all be lined up nicely in order. And your constant term, if there is a constant term, will always be at the end. Good. So we've been working with algebra tiles, collecting like terms. Now we're doing an example, example 6. It's our last example for the day. We're going to be doing it without algebra tiles. Okay? So we're just doing the algebra side of it, just the written mathematical stuff. It says simplify.
This is example 6, right?
This is example 6. Simplify. A, we have 6x plus 4 plus 8x plus 3. Let's say off to the right, we're going to do a few notes for ourselves. So you need kind of like a column here. Doesn't have to be half the page. It'll be a little bit less than half the page maybe. We're just going to give ourselves some notes so we know what we're doing. When, it's strategy, it's steps to doing it. When collecting like terms, first, group or identify like terms. So I like to do that with different types of squiggly lines underneath each term that gets grouped together. After we do that, we're going to add or subtract like terms. We've done that before. We called it combining like terms. Then we're going to apply integer rules. So I guess this is while we're adding and subtracting like terms. In order to do that, we apply integer rules to the coefficients of like terms. I'll explain that a little bit better when we get to it. So apply integer rules to the coefficients of like terms. It just means the rules that you use for adding and subtracting numbers, integers, you also use for adding and subtracting the coefficients of the like terms. But on top of that, you need to remember, do not change the variable part. If you're adding 3x plus 5x at the end, you're still going to be left with x's. You're not all of a sudden going to have x squares or x cubes or whatever. Does that make sense? If you're adding x's, they stay x's. If you're adding q cubed, they stay q cubed. Okay? So here we go. Step 1, group or identify like terms. What are the like terms? So we have 6x and 8x. Again, I'm just going to choose a straight line for them, and I'm going to keep this addition sign with the 8x. It's positive 8x. Any other like terms?
4 and 3.
The constants. I'm going to pick a new type of line for them. Okay. Now I need to add or subtract like terms by applying integer rules to the coefficients and keeping the variable the same. So 6x plus 8x, all I need to look at is 6 plus 8 is 14, and I'm dealing with x's. Okay? This is another reason you can't combine like 8x and 3, because this guy doesn't have the same variable. So if you added the integers, the coefficients, and then kept the variable the same, it'd be like, oh, what variable do I keep, x or no variable? They're not the same. Can't do it. And we add our constants, 7. So you've got 14x plus 7. Okay? I'm going to show you just quickly a second way to do this. Second way to do A is to say, okay, I have all of my terms here, and I can line up. Another way of grouping your like terms is simply to line them up. So I have 6x, and I have 8x, and I have plus 4, and I have plus 3. And I could add that up that way. Okay? This positive sign stays with the 8x, so now I have 14x plus 7. See how that's exactly the same? Two different ways of grouping like terms. Okay, this way lines them up so that you're just doing addition how you already know how to. I prefer doing it this way. I think it's faster. But your call. B. B is 2b minus b plus 7 minus 8. And we need to, step 1. By the way, what makes this one more challenging than the first one?
B.
I ain't that challenging.
It's a 1.
It's got some negatives. Okay, you have an invisible coefficient of -1 here, but the negatives make it more difficult. In this one, the terms are already grouped together. We have our b terms, +2 and -1, and we have our constant term, +7, -8. So again, we can do it this way. Just say, oh, okay, I have apply integer rules to adding and subtracting the coefficients and keep the variable the same. 2 minus 1 is 1, 1b.
So it's
+7 minus 8,
Would it be
No,
minus
it's negative.
negative?
It's negative.
B.
Yeah.
Right?
It's a negative 1.
+2
Oh.
minus 1.
Yeah, but there's a negative
2
1
minus
right there.
1.
No, there's a negative
It's
right
not a
there.
negative.
No, we're not talking
You're
about
just
that.
minus
It's a
the
negative.
There's
or
a
a
coefficient
minus.
1 right there, you said.
Yeah,
Yeah.
that's
Yeah.
why. It's an
Oh, yeah.
invisible 1.
We know it.
So you got 2 minus 1. Okay, if you want, we can draw it out. You'd have 2 positive b's. You'd have 1 negative b.
It says we're
What are you
allowed
left
to
with? Positive b. Okay?
They were talking the other part.
Let's talk about our constants. We have +7 minus 8. It's going to leave us
Would
with
it be negative B?
neg.
It's
Yep.
1.
So we're left with -1. Okay?
Because we're adding a positive.
No.
Do I need this 1 as a coefficient in front of the b?
Yeah.
No, so I could rewrite this without that. It's just b minus 1. Okay? Again, if you wanted to practice doing it the other method, if you wanted to line it up, you'd have 2b minus b, and you'd have +7 minus 8. And you could see 2 minus 1, and you can always kind of draw this in if you want. 2 minus 1 is 1b, I'm just left with b, and 7 minus 8 is -1. Okay? Same exact answer. Good. I'm going to clear just my left side. I'm going to leave our directions up here in the right. And we are on to C. C is a bit longer. C gives us 3r squared plus 2 minus 6r plus 9r minus 3r squared. So whenever we have something like this is where I like to use my lines underneath each like term. Someone identify like terms for me.
3r squared and
3r squared and -3r squared. Remember, the sign has to stay with the term. Any other groups?
6R.
-6r. Yeah? And +9r. And this constant's all by himself. So we're working in descending powers of r. That means start with the highest degrees and work down. So we've got +3r squared and -3r squared.
R squared.
No, it's not 0.
It's 0. Okay? If you have 0 r squareds, you just have 0. If I were to write this, remember that means 1r squared. Well, 3 minus 3 is not 1. Okay? So we can just leave that guy right out. They canceled out, and let's move to our r terms. We have +9r and -6r.
3r.
It's going to leave us with 3r, and our constant term comes down 3r plus 2. Good job. Last example here, D, 0.5 m minus 4.5 n plus 0.7 m plus 4.5 n, as in Nancy, and negative minus 1.5 at the end. All right, same strategy. Identify like terms.
0.5 with 0.5m with 0.7m.
Okay, so we can group our m's together and keep the positive sign in front of it. Any other ones?
Yeah,
Negative
The
1.5
n.
And we can group our n's together, keeping the signs with them.
And those
And
cancel each other.
our constant just stays there. Now we apply the integer rules to adding or subtracting the coefficients, and we keep the variable the same. Let's look at our m, as in Mary first. 0.5 plus 0.7, 1.2. M's, our n terms, our Nancy terms,
0.
they cancel out, 0, and bring down our constant, negative 1.5. Okay, like terms have identical variables.
Wait,
You can simplify a polynomial by adding or subtracting like terms. That's called collecting like terms. Sometimes we didn't show it, but it can be helpful to think about. I'm not even going to say this one. That's all you need to know. Your practice problems are found at the bottom of page 21. They are from page 171, numbers 1 through 43.